solutions. But trying to copy a human and get the intelligence of a human is even beyond the scope of Elon Musk and Google at the moment. It is pretty tricky. And the way we do it, neuroscience. Anybody parents and neuroscientists? Okay. Good. They're idiots. They put you in a scanner. Scanner is a product of electrical engineering. In fact, the prototype was 9 miles away from here at a firm called EMI. I went to visit a student once down there, and I like looking at skips, and there's some interesting rubbish in the skip. And I said to the guy I was visiting, "What's that in the skip?" Oh, he said, "That's the prototype of the scanner." They couldn't develop it, but of course Siemens came along and made billions out of it, and it's changed humanity. Anyway, a neuroscientist will take a scanner, will put you in it, wants to find out how the brain works from a top-down approach. So they play nice music and see where the electrical responses are. They show you a picture of your mum, and you get sentimental and homesick. Different responses. They turn the temperature down, and you get cold. They put all sorts of stimuli on you and see where the response is. Oh! They frighten you. Response there. And they build up a picture of voltage activity in the brain, dependent on external stimuli. And they think they know how the brain behaves. Oh, that's the fright area, that's the temperature area, that's the affection area, that's the fear area, and so on. And they've identified this way about 60 regions of the brain. But that gives you no understanding of what's going on. Okay. It's like taking a phone. My phone. Taking a phone. I want to find out how the phone works. So I'll put a heat detecting device on top of the phone. I get you to call me. It gets hot there. Oh, that must be the phone call part of the phone. I do a Google search. That part gets hot. That must be the internet part. So that's not understanding the electronics of that phone, is it? It's stupid. That's the level of some of our friends in I used to be anti-mechanical, but I think I'm getting more anti-medical as I get older. So, what is the way forward? And also, if we want to do physical experiments on the human brain, would you like to assist me with physical experiments on the brain? Go cooperate. Yes, she said yes. Take her in the lab, little circular saw around the skull, carefully remove it, see the globular mass inside. Let's experiment with it. Let's put a voltage in there. Oh! That's the foot controller. Another voltage there. Bang! That's the punching controller. It would be silly, wouldn't it? Because what you've got up there is 10 to the 9, 10 to the 10, 10 to the 11 cells. Huge complexity. So that's not going to get us a solution. The way forward, I think, is not to deal with the complete system, but do a bottom-up approach. And when I say a bottom-up approach, I don't mean a physical bottom-up approach. Take a simple cell. The simplest cell in the brain is a neuron. It has inputs, which are voltages. It has a blob, which processes those inputs. And it has a single output, which goes to other cells. So that is basically a neuron. It's been known for about 80 years. And trying to get models of that, how that behaves, seeing what its properties are, putting cells together and seeing what the emerging properties are, and getting an understanding from the bottom up, I think is the best solution. Of course, computer scientists who think they own AI these days, they're just using programs. And I'll give you an example of a project last year. I wasn't supervising it, but the guy was talking to me. He was trying to do face recognition with neural networks. And he was trying to detect your face from everybody else's. So it's a one-menu classification. And he trained the system on the target face. He trained it on some which weren't the target face, and he tested it. And he got 40% accuracy for detecting the target face. Well, it's better than nothing, isn't it? He came to me, he said, what do you think? I said, well, I can immediately improve the performance to 60%. Oh yes, how do you do that? How do I do it? Any suggestions? There's the target face. I get a high response to the target face. Before I was saying it was the target face, I got 40%. If I say it's not the target face, and everybody else who's not the target responds, 60%. That's silly, isn't it? Another interesting thing you can do with neural networks. Anybody want to win the lottery? Anybody want to win the lottery? No? Okay, I've got a good scheme. Last 3 tickets I bought didn't win. They're 6 element vectors, 6 numbers. And they were positioned in 6-dimensional space. And I also kept an eye of the winning lottery tickets in the past 3 weeks. So I've got 3 winning and 3 non-winning. And I train a neural network to separate them. And it does. We're in the money. I've got a winning lottery ticket detector. I tell you what, I'll give you a recommendation. £5 is low. I'll make some money. Is it worth investing £5 to know which is next week's winning lottery ticket? Call me God. Oh. Of course it doesn't work. But these are some of the weaknesses of neural networks that people are not understanding. Last week, talking to Paul Kaibo, you know Paul Kaibo? Good? He's a lecturer here. He's a physicist.
Level 1 data information systems, databases lecture. He was teaching you.
Okay, well, remember Stonham in the first year? Oh, thank you.
Do you remember me in the second year?
Right, Paul, his son works at Oxford University on autonomous vehicles. Pretty good team. Got a system up and running to drive a Ford Focus in London. And demonstrations, fairly standard internal combustion engine, not a electric car. And Paul was invited to have a test ride as a passenger. And I think Paul's mother, who's a very old lady, was also in there. And he got him in the vehicle and they drove around the South Circular Road in London. And he was quite impressed. They had an emergency driver who sat there with a big red button in front of him, but he just sat there. And the car indeed negotiated the junctions. And Paul said it was a bit boring, not the sort of fun that you'd want in a nice sports car with your boyfriend, girlfriend, or somebody in between sitting beside you, tearing down the motorway. There wasn't that sort of excitement. But it got round, it didn't hit anything. It behaved properly at about 15 miles an hour. I was sort of impressed with this, because I respect Paul. And I said, yeah, I'd quite like to have that vehicle. I haven't got it with you, have you? I'll see if it can drive me home to Oxford tonight. He said, oh no, it can't do that. It might avoid all the collisions and whatever, but you have to take it round the course it was going on 20 times to train it. It will only work on that particular piece of road. So still a lot of improvement to go. And we as humans tend to underestimate the difficulty of some of these implementations. You go back many, many years to character recognition, recognizing handwriting. If you were around 50 years ago, you would have a bank account with a checkbook. And the checkbook, the checks could be read automatically, 1970, 1980. And they did that by taking the numbers 0 to 9 and stylizing them in a very specific way. So that certain parts of the character was a big bar. Look at the slide.
Yep.
Yep.
So, shall we get rid of this? Try now, whiteboard.
So a 1 might be a bar like that. Very precisely printed. A 2 could be this. A very thin line there, a big bar there, and a line there, and a line there. And the idea was that you would ignore the thin lines and look at the thick lines, and each one would be different, and you could recognize them. And that worked pretty well for 1970, 1980 for your grandparents. But as soon as you start going to handwriting, or even printing with the fonts, how many fonts are there on the computer at the moment? 200?
And I just ask you, how many of you understand your own handwriting?
Yeah, when you come to handwriting, there's one.
Some of you
there's
are not
two,
sure about all this.
There's three, two. We all recognize them as twos, but they're certainly different. And so that was a big step to get to handwriting. So recognizing the whole world is quite a challenge. But we can do it, so don't lose heart. Right, how are we doing for time? That's halfway through. Right, some of the problems with AI. Big data. Heard of big data? What is big data?
In your understanding, when we say big data, what is it?
Come on, your life depends upon it. What is big data?
The data set with a large amount of information.
Big data! If any of you were in the foundations year, what is the unit of electrical power? Answer?
Yes.
What is the unit of electrical power?
Yes.
What is the unit of electrical power?
Yes.
What? Got it? What's the cry of the existentialist? What's it now? Oh, no, I won't go that one. Right, so, big data. Now, traditional analysis, dear old Newton, how do we clear this? Rub it out like a real thing. Dear old Newton is interested in motion. There is one of the simplest equations of motion. S is distance, t is time, and u is the constant velocity. Spacecraft going to Mars in deep space, traveling at constant velocity, how long will it take? Now, if that is true, that is a deterministic system. And how many tests can I perform on that equation? Billions, trillions. If u is 1, let's keep it simple. 1 kilometer per minute, 1 kilometer per second, whatever. If I travel for t equals 4.372 seconds, how far have I gone? 4.327 seconds. If I travel from 5,200 meters times 5,274, distance is the same. It is a deterministic system. It applies to all circumstances. Or does it? When might it not apply? Yeah. When? Oh, no. When does that equation not hold true? Oh, no. It's a little smart ass who came along about 80 years ago called Einstein. Is that a clue?
Speed of light.
Traveling in a train. The train is going at half the speed of light. It's a French TGV, better than English. And I'm in the corridor facing the direction of travel. The train is traveling at half the speed, and I have a cricket ball, and I throw the cricket ball in the direction of travel, and I'm a pretty good thrower, and I throw the cricket ball at half the velocity of light. What is the speed of the ball with respect to the Earth?
Speed of light.
No!
Zero.
It actually is about 3/4 of the speed. See, you wouldn't get that effect in online, would you? I swear at the screen and I get no reaction, and I'm embarrassed being having you here. It's so much more fun.
You will not even attempt to answer this.
No, the answer is about 0.75 of the speed of light, because the actual relationship between distance and time at very high speeds is not linear, so that equation doesn't apply. Okay, where am I getting to? Deterministic systems are simple. We just solve the underlying theory and we can apply any data to them. But if we now come
Training.
Yeah.
You getting where John Stoneham coming? You have a neural network, you have inputs and outputs, yeah? You have the output. If you want to derive this equation, the training set must be quite very large to make sure that you validate the neural network. That makes sense? And the truth of this equation will be only based on the training data you have. You forgot to include some data, like for example, speed of light. Will the equation be true? No. So the training is very important.
And the architecture of the network.
Yeah, we'll get there.
Right, carrying on my story. Newton was easy. Maths is easy, it's deterministic. But we are interested in AI in pictures. The main source of data is pictures. Yes, you can have speech, you can have other telemetry measures, but the main source, the greatest source of data is pictures. And if I were to take a single pixel, and the encoding was black or white, 0 or 1, it's quite obvious that there are 2 pixels. The black pixel and the white pixel. If I go to 2 pixels, how many pictures can I display, black or white, for those 2 pixels? 4. Yeah. If I go to 3, 9.
Really?
Here, for 3 or 4?
3.
3.
I've got 9 here.
8.
9. I will go switch into German, and the answer is 9. Which one? 8. 4.
16.
Right. N pixels.
2 to the power.
2 to the power n. Let's stick with that. 2 to the power n. Let's now take a trivial picture, and I can just about draw it if I have a full screen. Can I? Yeah, give me a whole screen.
Why are you not taking notes? Are you
Right,
enjoying, yeah?
that crazy picture is supposed to be a 16 by 16, whoops, I'm having 14, 16 by 16 pixel array. I can draw it. And this would be a single pixel. Have we got a different color?
Yeah. You have a box there. Try to touch the notes because this module is quite a lot of.
Is this being
You have
recorded?
fun, but once you leave, these type of questions can come on exams.
Right. There we are.
So it could be good to start to take a pen and paper and start to put some small notes.
There's a single pixel in red. The question is, and this guy's going to answer because he's smart so far, how many different pictures can I display on that array?
2 to the 16 times 16.
Which is
2 to the
256.
32. 16 times 16.
256.
256.
2 to the 256 pictures could possibly occur on that array I've drawn on the board. Is that a big number?
Yes. Very big.
And we are looking only at the moment is black or white. We are
Yeah.
not taking colors yet.
I don't understand powers. I can't imagine the size of them. So I'm going to make the approximation that 2 to the 3 is 10. So I can divide the power and express it as a power of 10. And I am going to approximate that to 10 to the 80, dividing 256 by 3 roughly. 10 to the 80. Is that a big number?
Yes.
Pretty big. You might recall in level 1, I don't know whether it's a calculation of you lot, but we have done it in the past. We have calculated the number of electrons in the universe. and you're hard pressed to get it bigger than 10 to the 80. Wow! That is, on that space, you can draw more pictures than there are electrons in the universe. Now, most of the
And
pictures,
black to in white only.
black and white, and only 16 by 16. The face on there would be terribly low resolution. That is big data. And we don't know how learning systems are going to perform with the totality of data. Now, most of the pictures there will be random noise. But the total universe is huge. So, when Elon Musk gets on the news, as he did last week, and said our car collision pictures are absolutely guaranteed to be foolproof, we have tested it on 250,000 collision incidents. And everybody sits back and says, oh, that's like 250,000, we must be as safe as houses. The pattern space for his cameras, it is not going to be a 16 by 16. That's used to hi-fi, this is a high-tech. It is going to be 4,000 by 4,000. That's going to be a 16 megapixel image. And the single pixel is going to not be black and white, it's going to be color. How many bits in a color pixel? RGB.
256, yeah.
256 bits of red, 256 bits of 256 levels of red, 256 levels of green, and 256 levels of blue. That is 8 bits resolution for red, 8 bits resolution for green, 8 bits resolution for blue, 24 bits, and the number of states is going to be 2 to the 24.
Have you understood the calculation?
Yeah. So, dear old Elon, you haven't quite done enough testing, because the number of patterns on that pattern space is going to be the number of states of the pixel. In before it was black and white 2, now it's going to be 2 to the 24. And that is going to be raised to the number of pixels because they are all independent. And that is going to be raised to the power 16 million. Can't even write it. I have to write it as 16 times
M.
10 to the 6. Now get your calculators out and see if you can calculate that number.
I won't do it.
Don't bother. If 10 to the 80. So, his 250,000 tests on his collision system might have worked on the test, but it was only a fraction of what could happen in the real world. So these are sort of some things we will be looking at as criticisms and possibly looking for ways of improvement in your measures. Better talk a little bit about the course. It's going to be divided into 2. I'm going to be talking about basically 4 things in learning systems. One is heuristics, rules. If it looks like a duck and it quacks like a duck, it is a duck. It will work for some image processing tests, but not all. That's a rule. The other is learning systems, conventional learning systems. We want to survey what your political views are or what you think of the university. Give you a questionnaire, strongly agree, strongly disagree. 20 questions. The answers to those where you score between 0 and 5 becomes a vector point in pattern space. And we're going to use distance to measure similarity. Interesting, not perfect, but interesting. And so I could do a questionnaire on you guys. I could take you as the query. When I say query, I mean it's an inquiry, not anything else. Take him as the inquiry, got his vector. And and I measure the distance on those set of questions between him and all the rest of you. And I find the closest distance. And the implication there is the closest distance is a person just like you. And the closest distance may well be you. So do you like him? Say no. Say no.
I know.
Right, so it doesn't work straight away. But that's the sort of thing that's done in profiling people. And the Americans have used it for election, predicting who they vote for and targeting. All these things come from the learning system. So that's a traditional learning system. I will then look at the neural networks, which I think is the big thing. There will be the analog neural networks, which is using a vector model of the neuron. Very simple vector mathematics, so don't get scared. And that has been around since about 1950, starting in America from a couple of guys called McCulloch and Pitts. And it has problems, interesting problems. But we want to understand those. And you won't understand the problem, the underlying problems, by just using a simulation. Just get results. So I want to make you guys smart. Then I move on to digital neural networks. Now, digital neural networks are particularly a favorite of mine because that's what I've been working on for 60 years or 70 years. And if you go into the Science Museum in the Whitton Mathematical Gallery, there's a permanent exhibition. And there is a device which recognizes faces in there, which is about 1990, before you were born. And that bears the name Wizard. And it's in an exhibition of breakthrough computing developments since the year dot. And the Mach 1 machine is in there. There's the Babbage machine, which mechanical engineers tried. And we've got our machine there. And the device is called Wizard. And WI stands for a very good PhD student who was at Brunel, Bruce Wilkie. The A stands for Alexander, which was head of department, and a colleague of mine here at Brunel. RD is recognition device. The word wizard must be spelt with an S. Now, I've forgotten what the S stands for. Modesty prevents me from saying it. So that will be covered. And that is still a pretty interesting technique. And again, my bias comes out. Analog systems, oh, forget them. Analog neural networks, no future. The future is digital. The future is logic. And what is the basis of using logic for a neuron? Take a single neuron. The medical people will say the electrical activity on the inputs is firing. It's a neuron like that, and all of a sudden it starts spiking and you're excited. And then it calms down again. So it's firing and not firing. The output is firing and not firing. Something goes on in the middle. The inputs are binary states, 0 and 1, firing or not firing. The output is a binary state, firing or not firing, 0s and 1s. What is the obvious candidate function in the middle? Binary inputs, binary outputs, logic functions. Yeah. And then, towards the end of the course, I will look at image processing, which is easier because we know what we're doing. It's a bit like Newton. We've got the formula, we've got the equations, what image processing. So that's my half of the course. Tatiana, you tell them what you're doing.
Now, I saw your faces a little bit when John was talking about neural network of 60, 70 years old, and I know some of you are looking for conventional neural networks, something that is currently boom everywhere. Some of you coming back, I want to be data scientist and so on, yeah? The course which is delivered to you or by John is for you to understand how neural network works. If you understand how it works, you will be able not only to apply any CNN or capsule networks, any latest advances, you will develop your new ones and validate on this. So basically, what John is giving you is foundational basics for understanding how everything works. You have understanding, you apply. Okay? I think you enjoy now with John speaking, so I think this is our style of the module. So I don't give you such good memories of me teaching to you. But believe it or not, this is a module where, when I'm having fun and I'm really your friend and you can relax. So forget about all my tough looks saying you have to pass this, you're going to fail this, and suddenly become super friendly. You know, so all these nightmares, they sort of disappear.
She's quite nice, really. She sometimes buys me lunch.
So apparently. And the reason for this is that I'm not the John Stoneham, not working for 40 years. 50
Get
years
on with
and
what
so
your
on.
stuff is much more exciting than mine.
I work in the area more than 25 years. So still a little bit, but like twice less than John Stoneham. And we are going to look not only neural networks, because artificial intelligence is not only neural networks. At the moment, you have a boom on neural networks because there is a major compatibility between computational power we are having at the moment and ability on neural networks. But later on, in order to us to design intelligent systems, we will need to get more complex systems, more hybrid systems. And artificial intelligence refers not only for neural networks, machine learning neural networks, but for any algorithms which have been inspired by nature. Okay, and there are a lot of algorithms which is inspired by nature: genetic algorithms, ant algorithms, bird algorithms, bee algorithms, and so on. So name it. So we are looking for the way how nature behaves, and we're trying to simulate in computational science. And this is what intelligent systems are. Surprisingly, they work really well in solving a lot of problems. While you're going to look on the problems on classification, image classification from neural networks, we're going to look with you on problems on optimization, design, on genetic algorithms. And I'm going to give you the basic foundational knowledge of fuzzy logic. Fuzzy logic helps us to start to use a lot of application in control theory. So doing electrical engineering degree, yeah, so computer system engineering and so on, you need to start to understand how the control systems work. And fuzzy logic is normally helps us to understand and implement more accurate responses of fuzzy logic systems. Fuzzy logic systems have been used quite for a while already in the application areas, and it has been hybridizations in different variations, with genetic algorithms, with ant colonies, with neural networks, and so on. So there are all varieties of these. And for you to understand how all this hybrid system works, you need to know foundational basics. Okay? That's why we will touch only two main points, but as soon as you understood the nature-inspired algorithms, how they work, you will not be afraid to touch anything else. Does that make sense? We'll be concentrating on genetic algorithms in the first term, and we are going to concentrate on fuzzy logic in the second term. Now, genetic algorithm. What do you think it's all about? Anything? Yeah, come on.
Sort of like survival of the fittest, where you test a bunch of things and
Yeah.
traits from the ones that are good.
Yeah, we're speaking about survival of features and so on. How do we define each of you as a person in survival of features? How do I know that, for example, how you look like without looking at you and so on? What I will be using in evolution theory? Biology, guys? Darwin theory? DNA. We'll be using DNA. Each of us is completely different. Yeah, my DNA with my red hair, you cannot mix up with anyone who you have, for example, black hair. Yeah, so it's red hair stays with red hair, regardless where it is, and it will be all marked in DNA. Yeah, in evolution, this is how it works for human being. In genetic algorithm, we are going to do exactly the same, but we are going to solve as solutions. We will represent solutions as DNA. Okay. So we'll start to look in Darwin theory, but from artificial intelligence point of view. So we'll start to have a look how solutions can be done, how we can represent, and how survival of fittest is actually works in genetic algorithms. Okay? All these algorithms, surprisingly, now you can see a boom of artificial intelligence and mainly machine learning. When everyone is saying we're using in this application and so on, you will check your mobile phone, you will have tons of artificial intelligence algorithm running now in background. And it's not only neural networks. So it will be also genetic algorithms, it will be uncolony algorithms, and so on. Surprisingly, if I'll talk to, when I talked with students 5 years ago, and I will tell you that your phone is run by artificial intelligence, your car is run by artificial intelligence, everyone will be basically scared and run away and will stop using it. But for example, the control of engines, how much of petrol comes in the engine, it was implemented already in 1980s, but nobody ever admits that it has been done like this. Because as soon as one of the company will say that we control injection of petrol in engine by artificial intelligence, no one will buy this car because they don't trust it. So we don't know, and you don't know, quite a lot of products that has been implemented previously with artificial intelligence that we are working now. I remember the story of one of my students who was doing final year project in genetic algorithms, and he was constantly telling me, do you realize I'm not going to use it in the industry? It's just final year project, I want to get top grades and go away. Fine, do your final year project. So he has done final year project, he got top grade A's, gone. 6 months later, I'm receiving phone call. Hi, how are you doing? Very well. Where are you working? In Intel. What are you doing? Tatiana, you will not believe I'm using genetic algorithms. I never ever thought that the companies will use it, and apparently they use everywhere. Nobody knew about this, but it has been actively used. Nowadays, the situation is different because there is a boom on convolutional neural networks, everybody is saying it's the top and so on, yeah? So you want to know. And this module will help you to understand how the system works, okay? But also it will open up for you other artificial intelligence techniques that you will find and discover by surprise when you go to enterprise and companies to work in. But it will open up for your possibilities. We work very closely with industry. So we have quite a lot of grants, and we work on different types. Genetic algorithms, uncolony algorithms, imperialist algorithms, we all implemented all these in products for the company. So it's not only like I'm giving you because it's theory, we've done a lot of practical stuff. And we continue to work on this, okay? So for you, it will be quite a bit of insight. But remember, guys, in order to have a fun with module, it's a lot of terminology, okay? You will not understand what we are talking if you miss one lecture. Not because we are so smart and we just show smart, because all this terminology lays one on top of another one. And literally every week we are going to introduce more. You need to understand the basic layers of terminology to start to understand what we are talking about. Attendance is important, but doing exercises is important as anything else. You have to be present. You have to do exercises and listen to us. And get pen and papers. How many of you just written down in your notes now? Very few, until I remind you to do this. You forgot what pen and paper is for a year of being away from face-to-face classes.
Of course AI is going to be better for petrol control. What did the mechanical engineers produce 100 years ago? A carburettor, which was a hole with a pin which bounced up and down and changed the size of the hole that more petrol went through. Of course we can do better with that. Right, don't want to scare you guys. Reassurance. Yes, we are looking at biology. Biology, natural systems are fantastic for inspiration. I won't be operating on 4,000 by 4,000 coloured images. Too complicated. We will be dealing with 3 by 3 pixel images, or 4 by 4, at the most 5 by 5. And the methods that you use on them is what you will be examined on. If the exam next year that you take is the same as the one we've had in the past year, you won't have any choice on paper. It will be more of an assignment in the exam. And you have to do, to get 100%, Tatiana's half and my half. So it would be a good idea not to say, well, I'm going to skip some stuff because Tatiana's stuff is
You
so
cannot
easier.
skip because
So
we have both of them.
Keep an understanding of both sides of the fence. I'm going to be relatively simple. We're going to be nothing like the real world. It's the principles and the way they extend to the real world and the problems that might occur, which is going to be important. It's so much more enlightening than just using a bloody computer program and pressing the button go. and see what happens and get some answers. What the hell is going on? I don't know. The computer says this is it. That's no way of understanding. On Tatiana's side, she'll be dealing with genetic algorithms, for example. They are inspired biology, but we're only dealing with a tiny resolution of what happens in nature. Tatiana's genes, not her genes, but genes she's using in her lectures, could be 16 bits long or at most 32 bits long.
It will be very simple exercises, just for you to understand how everything works. We will be testing understanding.
What have you got in biology? Well, take a single cell, it contains DNA. Can I have one of your hairs next to your head, could I?
Don't touch my hair.
Something in my hair. Oh, get my hand out. Oh, there's one.
It goes faster.
A human cell, 1 micron cubed. It's about the physical size. In it is DNA. DNA is a double helix, extremely complex chemical, most complex in the world. Nothing's more complex than DNA. It is about 30 billion. How the hell did it produce? I don't know. But that is coiled in that cubic micron. And if you were to take the DNA out and stretch it in a straight line, it's simply carbon, oxygen, hydrogen, nitrogen, and a few phosphorus and manganese atoms in a particular order. And if you were to stretch that DNA in a straight line, it would be about 1/100th the thickness of that hair. And how long would it be? So they say, how long? About 2 meters long. And that's all wrapped up in a single 1 cubic micron cell. And the coding in that DNA is about 30 billion atoms. So again, I'm only touching the surface on resolution, so is Tatiana. Understand the fundamentals, and you can get some idea of how the world behaves. And the final thing I would say to you, if you're going to do PhDs and projects, look at research papers, be skeptical. Don't believe in neural networks all the performance figures. Because if I'm testing on a data set, and I'm testing on an unknown set of patterns which haven't been seen before, and one of them is wrong, I can swap that, put it in the training set, run the experiment again, and it will work. So people, they're not being dishonest, but they always publish their best results. And they're not always scaling up to this complex world we're operating in. And don't give up, because although the history, go back to the 1940s, Turing and people like that, computing was just starting in 1942, it has gone up exponentially without a hitch. And what we've got today in terms of computing is pretty smart. AI, Turing was an AI man. The Turing test, which was 1940s, which is still used today. There was interest in AI, and it didn't work, and it dropped back. There's another wave in the 70s, another wave in the 80s. And about every 10 years, we've had a huge wave. And the wave we've got at the moment is the biggest.
And you're on the top of the wave.
There was a wave in the 1980s, 1990s I think it was, military DARPA in the USA, funding research to recognize tanks. They got a fantastic pattern recognition system based on a learning system, recognizing tanks on their property, every tank, every weather condition, whatever, perfect results. And they sold it to the military. They took it out and installed it in operations, which was the desert or somewhere different. It didn't work at all. It didn't work. It was hopeless. It caused a complete lack of confidence in AI. And why? What had gone wrong? In a picture, you're the tank, you're only a small part of the total view. What was the system had it learned to do? It had learned to recognize the background. And of course, for humans, we're much smarter, because I'm looking here, I can just see a blur there, which is you. And if I really want to recognize you, I come in close. And the eye has variable focus and variable resolution, which cameras in the main don't have. So lots of work to do. It's quite exciting. It'll be quite challenging. 5 years ago, we never had a failure in this module. But students have got worse, and conditions have got worse.
But
than
the
this.
reason
But
why-
I sense you are a brilliant lot. So I
No,
sense
stop,
you're
stop,
going to
stop.
do it.
5 years ago, we haven't got any failures in the moment, and the reason why in the module we haven't got any failures, we had 100 attendance in every single lecture. All students who attend all the time, all lectures, they get top grades. We started to see students stop through attending or just sleeping through online. Yeah, this doesn't work. As a result, your progression goes down. In our module, everything works well only if you are present. You go, you do exercises, you write down. I can really see a lot of people forgot what that means to take lecture notes. It's important to write the lecture notes. It was a science proven that you will remember material better if you will take pen and paper and write it down. And actually, writing down on paper, not on iPads and anywhere else, because your memory works about remembering the pages.
Your learning system, you've got to learn through input. You've got to input the information. You've got to think about it. Right, what's happening now? When are we next lecturing? How are we
Next lecture
lecturing?
is on Thursday. It's online lecture.
Online.
And if you will have a look just for us, timetable is quite easy. We have 1 week face-to-face, Monday, Thursday, and 1 week online. 1 week is face-to-face, 1 week online.
But this week should have been online. but we've got
This week
face-to-face.
shouldn't be online, but we try to put face-to-face. We do have 18 people online listening to us at the moment, so.
Okay, hi guys. Didn't know you were there. You're missing out on the emotion.
But you could really see like so how much difference, like you've been online for a year. How does it feel like to get back in face-to-face?
A lot better.
And I don't look scary anymore, yeah?
So who's taking Thursday?
What's your,
Kathy, I'll take Mondays.
okay, so Mondays is John Stoneham, and now I'll start
And
with you on
so in
Thursday.
week 3, we'll be all together in the class. On face to face.
No, week 2 face-to-face.
What's this week? Not
Next week, it's week 1.
right. We shouldn't be here. That's right. So
I will tell
this
you.
Is virtual. You tell me. Yes. You're the module leader. I do this thing.
Our lecture will be recorded,
We are currently recording the lectures, but to be honest, the quality of recording, yes, I don't know how it goes in face-to-face. And I strongly advise you to come to face-to-face because you get far more information. And I also, we work out with it with John. If you don't understand something, we can quickly adjust and explain to you again. In online, we don't see your faces. We don't see how much you learn. We don't see all this. Yeah, what's all this stuff? We don't see all this. As a result, we may go super fast and you don't understand.
And what is it like 100% personalized exam, unlike the other modules?
No. All exam.
It's all exam.
One assessment.
It will be based on your student ID, level 1. Remember level 1 Professor Stoneham exam? It was on your student IDs. We will do student IDs on your questions. So it will be very much similar style, but you must answer all questions.
And if you're on campus and I'm on campus, come and chat. Any problems? Talk about them. With you. Talk amongst yourselves about it. It's the way to learn. Take them to pub or whatever. Great.
So we will try to do our best for you to enjoy this module. It's the last year, so I'm not anymore scary, so I'm starting to become super friendly with you and delivering all this. But it also means, but make sure that we'll have some online tests on Blackboard as well to help you to understand the foundational basics and terminology, because we are building terminology super fast in both parts, and you could get completely lost within a couple of lectures. It's important to attend the lectures.
Okay, guys. Nice to see you. Go and have your lunch.
I'm enjoying.
How does this set up the tutorial?
Well, I believe this is what the students will see. So we have, it was 18 students. So something, thank you, Tiana and Joe. Hello. I was sorting out and anything, but it's all fine. And
Right. Now, why have we got 2 screens?
it's the same. It's duplicate.
Can we use different?
No, I cannot just.
So that
It's projected on both. Or you can use one. I put on both.
very sensible. Is
So, yeah, but it looks like it's, you see this is visualizer. The reason why it's done, you could put visualizer on one and you could put, for example, picture from the computer on another
So
one.
can I put a problem on there and hold it?
I don't know if online will see.
And then,
But-
then do the development here?
Yes, you could do, but you won't be able to do this if you need to have surface.
These people who set up these IT systems don't know what they're doing, do they? They don't know what we want. I mean, it's a two blackboard job. You put the problem or the diagram or the system up there and you do the
The
development.
reason why I have problem with this one because
one changed, that one
it's super
doesn't.
small, yeah, and when you're showing this and we don't see it. And we need to make sure that we enforce for the students that they attend the lectures.
Does this work with small pens?
Yes, we do.
Might be better.
But we need to go and get the small pens because I took the markers for the, what's going on? I took the, this is one of, I took the markers for the normal whiteboard, but
Yeah, that's better.
you see like what you write. Or for example, this one is, goes to the bin now.
No, that's okay, that's.
Yeah, these are better, yeah.
So we need to go and get the smaller markers.
Oh,
Because I took the big markers, but it's,
it rubs off.
but we need to get rubber with you because this is my set, you see? It's my.
Yeah.
And again, you see the problem is the cameras, we cannot adjust the cameras. They see only the small portion of the screen on online, but I think we need to reinforce the students must attend face-to-face.
So
It's, there is no any